Okay, picking up where we left off last time. So we were talking about this local test thing. And so the big idea is, really great things happen if you have a vector field that is actually a gradient. But how do you know if it's a gradient if you don't know what the anti-gradient is if that's not given, right? Okay, so what we found is that there's this fantastic test that a vector field is a gradient if and only if Green's operator is equal to 0. And we made what I think is a very clever, elegant argument that, roughly speaking, depending on how you look at it, this is a statement about circulations all having to be 0. And the point of view being, roughly speaking, from the point of view of how things happen as you go around a closed loop and that sort of thing. Whereas, on the other hand, this is a statement about how, again, circulations have to all be 0. Instead, from a point of view of how those circulations accumulate over the interior. Now, more details than that, of course, but I think that's a nice way of thinking about this. So, with that noted, again, local test. If you have a question about whether something is a gradient, this is how you can tell. Now, the cost of this result is that this only works in 2 dimensions, right? So what if you have a 3-dimensional vector field, and how do you tell if it's a gradient? And there we again have a local test, and the test is this time curl instead of Green's operator. Now, why is it curl instead of Green's operator? Well, there is, in the same way that Green's theorem plays a central role in identifying Green's operator as being the local test in R2, there is a 3-dimensional version of Green's theorem that is what identifies curl as being the local test in 3 dimensions. We just haven't seen that theorem yet. We will not too long from now. It'll be in section 7.3, and it's a huge theorem, wonderful theorem. And so we'll be able to fill in the blank later as to why this theorem works. But nevertheless, this is the test if you're in 3 dimensions. So let's see how this works in practice. Here's an explicit example. Here's a vector field. Is that a gradient? Now, it's hard to look at this vector field and just kind of see, what an anti-gradient might be. Right? There's just kind of too many terms. It's kind of too much going on. It's just not clear what the answer would be. But it is fairly straightforward to let's just compute the curl and see if it is or isn't equal to 0. So here we go. We're going to take this vector field, F, and we're going to compute the curl of it. And computing the curl, of course, now the curl is going to be a vector itself, so there's three components of the curl to compute. Quick reminder, make sure that you remember the formula for how to compute curl. I know it was a long time ago, chapter 3, right, a ways back, but very important to have that formula on hand. And as you start to compute, here's the first component of the curl, and look at this, it's already not 0, right? I don't even have to compute the other 2 coordinates because all 3 would have to be 0. This one already isn't. Game over. Did I see a hand somewhere? Yeah, go ahead.
Can you explain why circulations can't have a gradient?
Yes, right. So circulation, keep in mind, the idea of a non-zero circulation, let me go back, see where would be a good place to, this is actually a pretty good place, right? So here's a circulation, right? This is, circulation says, line integral, vector line integral around a closed curve, right? And if you let your vector field, if you think of that as potentially being a gradient, and think of the thing that it's a gradient of as being altitude, a circulation represents how much your altitude changes as you go around a closed loop. Now let's just think about intuitively about the way the world works. If you go on a hike and come back to right where you started, right? You park your car, you go on a hike, you come back right to where your car is, your grand total altitude change has to be 0. Does that make sense? I mean, yeah. Yeah, that's right. That's right. The total change in altitude has to be 0. And circulation is a way of measuring your total change in altitude. So that means your circulation has to be 0.
What
Yeah.
about examples like fluid? Could we do one?
Well, the point I'm trying to make is that if you look at it the right way, then it becomes clear. Now, there's lots of ways to look at it where it isn't clear, granted, right? But the point is, this is a way of thinking about it that does make it clear, right? Because if this vector field were a gradient, and if this anti-gradient were altitude, we have an obvious nonsensical contradiction. So this is the way to make this realization that gradient circulations have to be 0 is that this picture is nonsense.
Okay.
Yeah, right.
Thank you.
Yeah, sure. Okay. Let's see here. Right. So is this vector field a gradient? Well, it can't be. The curl would have to be 0, and it clearly isn't. I don't even have to look at the second and third coordinates. This is clearly not the 0 vector. Let's see a 2-dimensional example. Here's a 2-dimensional example. Let's look at this vector field. And, okay, well, 2-dimensional. Green's operator is our local test. We compute it. We get 2, which is not 0. So again, not possible for this to be a gradient. And this is basically repeating the Escher-Stairs story here. Hypothetically, if this vector field, if this were a gradient, that would mean that all of these vectors would be pointing uphill. Well, that's crazy. All of these vectors cannot be pointing uphill. If I start here at 1, 0 and go around in a circle, this would suggest I'm going uphill the whole way as I return back to the same point. And that's just nonsense. Right? Escher-Stairs and all that. Okay. All right. So what I'm going to call this is a geometrically satisfying confirmation that Green's operator being non-zero is inconsistent with it being a gradient. Okay, so now, weird story. I have to tell you all, I've kind of hinted at this a couple of times. There are different ways to think about some of the objects of multivariable calculus that we're talking about. And I made a vague reference when we were talking about coordinate line integrals. And specifically that even though they're not very convenient to think about, they are actually very powerful. And there's cool things that you can do with them that you can't do without basically coordinate line integrals. The reason for that is because coordinate line integrals are pretty much what differential forms looks like. Differential forms are just a bonkers powerful construction that allow you to do super cool, super powerful things, inaccessible otherwise. Wouldn't it be nice if we could actually approach all this material from the point of view of differential forms? We'd have all the power at our fingertips, and we could do all these powerful things. Trouble is, it's very sophisticated, it's very complicated, it's very intimidating, and it's just not appropriate for this class. So what I like to do is to take some, not all of course, but some of the really powerful constructions done with differential forms, boil off all of the formality and the rigor and the scary parts, and leave just kind of what's left over. And in a couple of situations, here's what you get left over. It makes sense for, again, sophisticated reasons we can't talk about, to take the gradient operator that turns functions into vector fields, and to take Green's operator, which inputs a vector field and spits out a scalar valued function, and to compose them together like I have here. Yes?
Can you remind me kind of what the green operator, or like what the value that it spits out indicates?
Yeah, it's circulation density. Yeah, so roughly speaking, Green's operator, if you're looking at a vector field, right? Green's operator, what you get will tell you in this vector field at a given point to what if I were to drop a leaf into that fluid flow, to what extent would that leaf kind of be rotating? To what extent would it be turning?
Okay, so if it's 0, then it's not circulating.
That's right.
And that's how you know it's gradient.
And that's what?
And that's how you know it can have a gradient.
That's how we know that it can be a gradient of something. That's right. Yep. Yeah. That's right. That's intuition in that direction anyway. Yeah. Okay. Yeah, so I claim really good things happen. We've already talked about some of this previously. We talked about exactness. So if you have a vector field for which Green's operator is 0, that means it does have an anti-gradient. There is a function whose gradient is that given vector field. We talked about this back in chapter 3. Again, I'm not going to be able to tell you why in the sophisticated sense. But in fact, this is the local test business that we were just talking about. So we do have a geometric sense of why this is. I like to point out, oh, by the way, I have a fuller version of this diagram here. This is I just typeset pretty much the exact same diagram, inserted some extra fullness, and this is in the it's on the course website, if I remember correctly, in the resources folder. One of those, or maybe it's in the class resources, class materials folder. It's on the website somewhere, and it's just a little bit roomier, a little bit easier to kind of work, and so I'm going to do my work off at this. If you've got gradient and Green's operator composed like this, that means you have functions, vector fields, and functions kind of in those places, if you will. And as it turns out, integrals of differential forms look like this in those contexts. And so in particular, double integrals, where do we do a double integral of a function? Well, we do a double integral of a function over a two-dimensional region. And likewise, where do we do a vector line integral of a vector field? Well, we do it on a curve, etc. So the way the pieces fit together, as it turns out, is that it makes sense to organize these objects kind of like this. Is that good for everybody? Okay. So what else is nice about this diagram? Here's another example. Let's look at the fundamental thermal line integrals. There's a point of view on the fundamental thermal line integrals that goes like this. We start with a function of which we take the gradient. We see there's a gradient in the fundamental thermal line integrals. We start with a curve of which we will be looking at the boundary points. We'll be looking at the A and the B, right? The A is the starting point, the B is the ending point. Together they make the boundary, you might say. With that set up, evaluating the original function on that boundary curve, like so, doing a vector line integral of the gradient on our original curve, like so. And we get the same answer either way. All right. So just to do that a little bit more quickly, if you push forward there, you push backward here, you get the same thing on both sides. Okay, now that's just a diagram change. That doesn't really bias anything. That's just arbitrarily we put things in a particular place on this diagram, and that's what it happens to look like. But check this out. Now let's look at Green's theorem. Green's theorem involves a vector field and Green's operator of that vector field. It involves a two-dimensional region and the boundary curve. And Green's theorem tells us that the line integral of our original vector field around our boundary curve and a double integral of Green's operator on our original two-dimensional region, again, are the same. The pattern is identical. This is mysterious. This is hard to imagine as being a coincidence, isn't it? That, again, fundamental thermal line integrals, in some sense, looks like this. And Green's theorem, arguably, is exactly the same. Same pattern, just in different places on the diagram. Really makes it look like these two theorems are connected to each other. So again, they are. There is a connection between these theorems. These are both actually special cases of a larger theorem. There's a sophisticated, only fairly recently discovered theorem, when I say recently in the big scheme of math, less than 100 years ago. Big sophisticated theorem that was discovered that shows that these are in fact literally special cases of the same theorem. Okay? So there's some very important sophisticated ideas underneath this seeming coincidence of a pattern that we notice when we lay things out on the page in exactly this way. Right? And that's why I think it's a valuable idea to kind of always think in terms of this pattern. And again, I won't be able to tell you exactly deep down why this is the way to look at it, but what we can see is that if you look at it this way, really nice patterns are going to emerge. Okay. I'm going to point out while I'm here another neat pattern. Going back here to, we know that there are certain special vector fields. Special vector fields being, for example, gradients. Let me do it like this. So gradients, aka conservative vector fields, otherwise known as irrotational. Now keep in mind, being a gradient means Green's operator is 0. If Green's operator is 0 and Green's operator represents a rotational aspect of the fluid, irrotational kind of gets right at that, right? Not, ir meaning not, right? So there is no rotational aspect. Green's operator is 0. And then we also had this idea of path-independent vector fields. And we know that, again, regularity issues aside, every gradient is path-independent and vice versa. And furthermore, every gradient, every path-independent vector field has Green's operator equal to 0. So these are 3 different features of the exact same vector fields. And I want to show you what this looks like on the diagram. Here they are, the special vector fields. They live inside of here. It's not all of these vector fields, but it's just some of these vector fields. And being a gradient of something, looks like that. Green's operator is 0, looks like that. And path independence, now I'm going to draw path independence here, and I have a way of writing it on the diagram that I think is satisfying. If I have 2 curves with the same boundary points, that's how I draw that, then they will give you the same value of the line integral. So this is my little sort of like diagrammatic representation of path independence. So that's not how I think about these things. Now you might say to yourself, okay, so fine, that's what it looks like on a diagram. Who cares? Here's why we care. Turns out there is a 3-dimensional version of this diagram. This is valuable for all the same reasons: differential forms, sophisticated results, powerful things that you can do, and all that. So for the same reasons that we have a structure we write things in that way, we're going to do it in this way down here. And that said, this pattern in 2 dimensions also works in 3 dimensions with the exact same pattern. And then here's where it gets weirder. It also works 1 dimension up. So we're going to be able to talk about special vector fields that are themselves curls of other vector fields, for which divergence will be 0, and for which there is a, oh golly, we're not really quite prepared to actually address this yet, but there's going to be sort of a surface version of path independence. And this pattern that works for certain kinds of vector fields regarding line integrals totally different results will hold the exact same pattern regarding special vector fields and their relation to what we're eventually going to call vector surface integrals. So a lot to be gained, again, from writing the pattern this way and being on the lookout for sort of consistencies of how ideas connect to other ideas in analogous ways on the diagram. Yeah.
So is this the same idea as when we talked about earlier on how like a vector field has two lives, kind of?
Yeah. Same thing. That's the exactness. Yeah, absolutely, totally. Yeah, lifetime of 2. Yeah. Okay. All right. So I just like to point that out. And then let's see here. Last thing, I've already talked through this stuff. Last thing I want to talk about concerning Chapter 6 anyway is how to find antigradients. This is just filling in a sort of a technical little detail that we glossed over previously. You may recall I stated, motivated the fundamental theorem of line integrals. I did an example, but in that example I just kind of pulled the antigradient out of thin air, right? And didn't give you any justification for where it came from. Seemed like a magic trick at the time, so I want to show you all how that works, and it's really a very straightforward process. So here we go. If you have a vector field and you want that to be a gradient, if it in fact is a gradient, modest observation, the components of the vector field have to be the components of the gradient. I mean, if they're the same vector field, they have the same components. Well, I can write that down as 3 separate equations. And now I can look at these 3 equations and observe that each one of these is a statement about a partial derivative, and we can take statements about partial derivatives and turn them into statements about partial antiderivatives. Again, not much to it here, but if the x partial of f is p, then the x antipartial of p would have to give you f. That's all this is saying here. Is that cool? Okay, so now there's a detail. I forgot about the plus c, right? Don't forget about the plus c. After all, anything for which the partial derivative with respect to x, if the partial derivative gives you f, then we're good. All right? Well, I know that just because of the setup, right? I know that the antipartial of p is going to have a partial that gives me f. That's by definition. So, but I am also allowed to add in here anything whose x partial is 0. Because if the x partial is 0, then this will still work, and this is, of course, what I really need. So what's weird about this then is this doesn't any longer have to be an actual constant. All it has to be is something whose x partial is 0. And yes, constants satisfy that rule, but also any function that doesn't have x's in it is going to have its x partial equal to 0. Right? So what we call this then is we no longer call this an integration constant. We call it a partial constant. Which I think, again, kind of makes sense. Okay. So what we really need then, we need for all 3 of these things to be the same function. I have the flexibility. I get to pick this C1 function of y and z to be whatever I want. Likewise, C2 function, likewise this C3 function. It could be whatever I want them to be. And if there's some way to pick these functions that makes all 3 of these green items all the same function, then that is my antipartial. My antigradient. All right, so let's see an example in action. Here we go. We want to find an antigradient for this function right here. Vector field right here. Following the rules on the previous page, I need to take the x antipartial of the first coordinate. I need to take the y antipartial of the second component, and I need to take the z antipartial of the third component. And now this is easy calculus, right? Antipartials, no big deal. It's just antiderivatives, right? And you're going to write down these things right here, that's, like I say, easy calculus. But it's easy to forget your partial constants. Now, at a glance, when you look at just what I have circled in purple right here, it's tempting to sort of give up the game too soon and say, look, I need all three of these things to be equal. They're obviously not equal. I guess we lose, right? But that's, again, not the question. The question is, given that you are allowed to let these functions be whatever you want, now is it possible to make choices of these that allow you to make these three lines all equal to each other? And this is not obvious. This is something that's a little game you have to play, and you just have to kind of see if you can make all the pieces fit. So let's start that game. I need, again, my goal is for this, and this all to be equal to each other. After all, f would equal to whatever those three things are all equal to. Okay, well, here's the thing. I see an x squared y there and here. All three of these purple lines are supposed to be equal to each other. If they're all supposed to be equal to each other, don't I need an x squared y here? I don't have an x squared y here. Am I out of luck? Is the game over? Did I lose? Not yet. I have the freedom to pick this C3 to be any function of x and y that I want. And given that I need an x squared y term, I'm just going to choose this to be x squared y. So I can make this work. So far, anyway, I've got other terms to look at. But so far, as long as I make the right choice of C3, I feel like I'm good. Okay, likewise. I feel like I need an xz term here. I don't have it, but I can make this xz. And likewise, I feel like I need a minus yz squared here. Again, I don't have it. Again, that seems like a problem, but wait a minute. I can make this minus yz squared. So having made those choices, look at this. Inside of each of these purple boxes, again, I need all three of these purple boxes to equal to each other. And as I have it right now, each one of those purple boxes is green plus orange plus blue. I think we're good. Right? And you can directly check that this has worked. If I can get this thing to, there we go. You can directly check that this, namely green plus orange plus blue, if you were to take this function here and compute its gradient, you would get this original vector field. Does that work for everybody? Everybody happy? It's a nice little method. It's very straightforward. Of course, there's some calculus to be done. There's some games to be played, but mostly pretty much straightforward. So this is how you find antigradients. Now, it doesn't always work. After all, it can't work if there is no antigradient. And let me remind you, we've already confirmed, let's see here, back here, we've already confirmed that there is no antigradient for this vector field. That much we know. If I were to try to find an antigradient for this vector field, it's not possible for me to win that game. So let's play and see how we lose. And how does this, question.
Sorry, going back to the one we just did, where you have
this one?
Or no, sorry.
Oh, sorry. Oh, this one here. Yeah.
Where you have the note. So
Yeah.
is that something that we would need to prove before we could start, or is that just kind of always?
No, if you wanna enter into a game not knowing if the cards are stacked against you, then you're welcome to take the chance and just see if you're on a wild goose chase or not by painful experience. Right now, case could be made, pros and cons. Like certainly in this example, I think it's pretty clear to see how the game works. Right, and you're gonna tell pretty readily whether or not you're in luck or out of luck. But there are some circumstances where this would be an ugly matter, and doing this in advance might spare you the difficulty of going through all that work.
Okay.
Yeah, right. Okay, so how does this method lose for this example here? Again, let's try to find an anti-gradient that we know doesn't exist. Okay, well, I'm going to have to take the first coordinate again and do the x anti-partial of that. I've got to take the color choices here. Second coordinate, I got to do the y anti-partial of that. Again, don't forget your partial constants. Right? Very important to have those partial constants in there. And again, thus begins the game. What function of only x can I put here, and what function of only y can I put here to make this and this equal to each other? And I claim you can't win that game. It's just a losing game. The cards are stacked against you. It's a wild goose chase. You lose. Does that make sense? Yeah, yeah.
Is it going to be like obvious if there's nothing like?
That's a good question. I hesitate to say always or never in cases like that. I mean, there are some, every so often I could imagine like some scenario where I still remember when I was in high school and I got into a heated argument with a friend of mine over who had gotten the wrong answer to a question because I came up with, it was an antiderivative thing, like we were doing an integral, and I came up with tangent squared. And my friend came up with secant squared. And I was quite sure that I was right, and ergo he was wrong. And he was equally confident. And of course we were both right, because tan squared is secant squared minus 1. So we both had the same antiderivatives, but we had written them just kind of in a different way. So I hesitate to say always obvious, right? But other than random bad luck with trig identities, it's usually pretty clear.
Because you just want them to like equal each other.
Yeah. I need these two lines to equal to each other, and so anyway, like I say, I hesitate to say it's always obvious because there's some tricky moments, but it shouldn't be that bad. It should be pretty clear. Okay. All right. Okay, so that's how to do antigradients and how you will fail when you're trying to find something that doesn't exist. And that finishes chapter 6. We move on now to chapter 7. Quick heads up, chapter 7 is going to be a lot like chapter 6. Chapter 6, after all, was about how there are certain situations in 2 dimensions where you can observe certain expressions can be thought of as accumulating quantities. Weirdly. Right? Circulation, accumulating quantity. So weird. Outward-oriented boundary flux, accumulating quantity. What are the odds? Change as computed over a curve, accumulating quantity. We get these wonderful accumulation theorems, very powerful, very useful for computing various things. Chapter 7 is going to be the same deal, just in 3 dimensions. What we're going to find, now real quick, I'll whip back over to my diagram here, and let me zoom in on the 3-dimensional part of the diagram here. There are various objects that we're going to have to understand. We're going to have to know how to plug points into functions. We know that. Vector line integrals in 3D, cool. We know how to do that. Triple integrals, not a problem. We know how to do triple integrals. What we don't yet know how to do is what on earth is this thing right here. This is called a vector surface integral. So we're going to have to talk about what does it mean to do an integral on a surface, and then furthermore, what would it mean and why would we be interested in the idea of doing a integral on a surface of a vector field. And so there's a fair amount of work that we're going to have to go to build up this idea of a vector surface integral. And once we have that, we'll have all the necessary pieces, and then we'll start creating cool theorems. Okay, so that's the big picture of where we're going. First thing I'm going to need to do is talk about how to parameterize a surface. What is a parametric surface? Big idea, A parametric surface is position as a function of two parameters. Now, this may ring a bell. In particular, I know you remember the word parametric. We've talked about parametric curves. Let me flash back real quick to where we talked about parametric curves. This goes way, way back to section 1.2, right? Long ago. And remember what a parametric curve is where you have position as a function of one parameter. So this idea of looking at position as a function of two parameters is a perfectly natural extension of this existing idea that we've already done a lot of stuff with. So let me start with an example that we've all seen before. This goes back to section 1.5. If you want to refresh yourself, remind yourself all the details of this. But this formula right here is a parameterization of a plane. Let me talk you through how that works. We start with, let's see here, we start with some point, x naught. I can characterize my plane by it being going through that point x naught and being parallel to these two vectors v1 and v2. There's a unique plane that goes through x naught and is parallel to v1 and v2. And with that in mind, starting at x naught, if I go some amount in the direction of v1 plus then some amount in the direction of v2, I am then just adding a multiple of v1 and a multiple of v2. Right here, let me do like this. Erase that. Right, orange plus dark green plus dark blue, and notice that gets me to some other point on the plane. And I'm just going to make the observation that if you allow yourself the flexibility to let S and T be whatever you want, in other words, if you can go arbitrarily far, or even in the other direction, but if you can go arbitrarily far in the V1 direction and arbitrarily far in the V2 direction, you can get anywhere in the plane by doing this. Does that make sense? Now, there was a particular metaphor that we used back in chapter 1, and the idea of the metaphor here was that you can think of the parameterization as kind of drawing the curve. I mean, think of t as being time, and then that position as a function of time literally traces the curve like you're drawing it with a pencil. And we don't really quite get that here because there are two parameters. You can't have two independent notions of time. It doesn't make sense, right? That's weird. So that particular imagination tool we have to kind of let go of. Sure. But nevertheless, you can certainly represent any point on this plane in this way by just making appropriate choices of S and T. Okay. All right. So what I'm going to show you now is various different tools for creating parameterizations. And there's various of them. Parameterizing surfaces is kind of like parameterizing curves in the sense that there isn't just a single way to do it. Right? It's tools for your toolbox, and be on the lookout while you're trying to parameterize a surface. Think about what tool might be most convenient, and get creative with it. So again, I'm going to show you the various tools, and an actual parameterization problem. You have to kind of fit the tools to the problem. Okay, so here's the first one, graph parameterization. You may recall, in fact, let me flip back to it real quick. Graph parameterization. In chapter 1, the big idea is if you have a graph, in other words, if one of the variables is a function of the other, whatever is your input variable, let that be your parameter. That was our Very simple little trick, and everything just kind of falls into place. If you just make this right choice, whatever is the input variable, let that be your parameter, and then the parameterization just kind of creates itself. Okay, the same exact thing works here. If you have a graph, in other words, if one of the variables is a function of the others, plural now, because there's two of them. Right now we're looking at a surface in space, so there are two input variables. Let those be your parameters. Simple as that. Totally analogous, just one extra parameter. Let's see an example. Goes through very nicely. Here's an equation. Let's try to parameterize that surface right there. How are we going to parameterize that surface? Well, good news. It is indeed a graph. Right? One of the variables, z in this case, is a function of the others. So these others being x and y, I'm going to let x and y be my parameters, s and t. I have now followed the instructions. I claim the parameterization now effectively creates itself. After all, if x is s and y is t, all I really need to know is what z is. But if x is s and y is t, then z unavoidably is s squared plus t squared. And we win. We have, as desired, position as a function of two parameters s and t. Works for any graph. Right? Super convenient, super handy, very often the right choice. Okay. Notice it does not have to be z. That's a function of the others. Here's an example where it's not z. In fact, here's an example where it's not even immediately given as a graph. Right here, the thing I want to parameterize is just given as an equation. Such and such equals 0. Right? This does not look at a glance like a graph. But it's easy to make a graph because I can solve for y. And sure enough, I have y as a function of the other two variables. Now again, following the rule, once I have it written as a graph, once I have one of the variables as a function of the others, the other two variables, this time x and z, let those be your parameters. Again, that's the real simple rule. If one of the variables is a function of the others, let those others be your parameters. And again, it's all over but the shouting. This formula that we have for y sort of forces our hand on what the formula for y is. If x is s and z is t, then y kind of has to be that business right there. Yeah?
This is all up to choice, right? Like you can make.
This what now?
This is all up to choice. Like
Oh, yeah.
X
This,
equal to S and Y equal to T.
yeah, absolutely. Yeah, there's no alphabetical order does not matter, right? So you can make x equal to t and z equal to s. Yeah, it doesn't matter. I mean, now to be fair, that will give you a different parameterization, but it is perfectly good still. It's just as good as a parameterization. Now, I will say in this case that we really do have to solve for y instead of x and z. If you try to solve for z here, it's not going to work. Right? Just algebraically, they just can't do that. And likewise, in this particular equation, likewise, you cannot solve for x. So we our hand is forced by the algebra to solve for y. But in some situation where you could have solved for either x or y or z, do whatever you want. Yeah. Okay. Now these are all what I'm going to call rectangular graphs. There are, of course, spherical graphs. And there are, of course, cylindrical graphs, right? Just instead of having a rectangular variable being a function of the others, it's where you have a spherical, let's say, variable being a function of the others. And I claim basically the same trick works. And it's arguably easier, even. It's weird how convenient this is. Notice I have here a spherical graph. Rho is a function of phi and theta. tempting to say it's only a function of phi. I suppose you could do that, but it is a function of phi and theta, and at good news, the theta dependence is easy, right? So function of phi and theta. And I don't even have to make any choices here. All I have to do is write down the coordinate conversion formulas. This is my spherical to rectangular coordinate conversion formulas from way back, right? Chapter 1, late chapter 1, as I recall. You write that down, and I mean, again, I don't really have any choice in the matter. Rho, after all, is cosine phi. And I've inadvertently won the game. I've inadvertently created a parameterization because I have position as a function of now two parameters, phi and theta. Very convenient. So yeah, nice little trick. Works in spherical coordinates, works in cylindrical coordinates, etc. Now, some people are a little uncomfortable about the fact that these are phis and thetas instead of s's and t's. I suppose if you really want to replace every phi with s and every theta with t, you're welcome to, but it's really not necessary. I mean, the only reason that you would need to do such a thing is to avoid a confusion of variables, right? So here, if I had left these as x and t, then arguably x is both an input and an output. I'm always scared well, in some sense anyway, when I have a potential confusion of variables. Here we don't. Phi and theta are now inputs. X, y, and z are outputs. I don't really see much to be gained by changing them to S and T. But again, you're welcome if you want. Okay. All right. Okay, next trick. Next tool for your toolbox. Let's see here. Oh, we have 2.5 minutes left. Let me hit the very broad points on this, and then we'll call it a day. Recall when we were parametrizing curves that we talked about this idea that vector addition is a really useful idea. In particular, we were thinking about a bicycle wheel. Do y'all remember the bicycle wheel with the reflector? And the reflector makes this jumpy, bumpy, kind of weird pattern as the bicycle goes down the street. We parameterize that curve. Very weird curve. By understanding it as a sum of two much simpler things. The axle is a simple story. Right, and then that radius, well, I guess it'd go this way. The radius is another very relatively simple story. And then it's just kind of details. Right. We're going to do the same thing here. This question concerns a admittedly weird scenario. I have a surface here. And this is somebody's head, and the hairs on this person's head are sticking out because, I don't know, maybe he was scared or something. Right? Or maybe he grabbed the static electricity, something like that. And so what I want to understand then is what is the shape of this surface that's formed by the ends of his hairs. In other words, his hair is making the shape of his head look different than his actual skull. Right? So how would I parameterize this purple surface? That's going to be our challenge, and I'm going to point out that the easy way to do this, surprisingly straightforward, is to note that points on this original surface are actually pretty easy to write down. It's a graph. Graph parameterization, nothing to it. These vectors, like this, they're just unit vectors perpendicular to a surface. We actually have techniques for that. That's actually not that hard either. And so these mysterious points here that we're trying to understand, how am I going to understand those purple points? No problem. It's green plus orange. That's all we're going to do. We're going to write down a relatively easy formula for the green points, relatively easy formula for the orange vectors, and we're going to add them. And we'll fill in those details next time. Y'all have a good Wednesday. See you on Friday.